We present a model comparison and visualization framework called Learning-From-Disagreement. The framework compares two binary classifiers in a model-agnostic and feature-agnostic manner. It includes 6 steps. The first 4 steps identify the disagreement between the two classifiers. Step 5 learns from the disagreement. Step 6 derives insight from the learning. Let's see how our approach works in a concrete problem. Assume we need to compare two classifiers trained to verify if the category of a merchant is a restaurant or not, using the credit card transaction of the merchant. This is a binary classification problem. The positive label is restaurant and the negative label is non-restaurant. For the input of LFD, we get two classifiers, a tree and an RNN model. Also, we have around 3.8 million merchants with their transactions in 2.5 years. At step 1, the two classifiers take the merchant's transactions as input, derive their own model features through feature engineering, and use them to generate the scores for each merchant. The scores reflect the probability of being a restaurant. Note that we do not need model-level details of the two classifiers, as our approach is model-agnostic. At step 2, we sort the merchants decreasingly by their two scores. A threshold is used at this step to decide the score cutoff. Instances with scores above the threshold are captured by the corresponding models. We use A+ and B+ to denote the instances captured by model A and B, respectively. Assuming the cutoff is 10% of all the merchants, meaning we consider the merchants whose score are in the top 10% as being predicted as restaurants. Then, the size of the A+ and the B+ cell will be around 380K. Step 3 joins those two sets of merchants into 3 cells. Both captured, A captured, B missed, and A missed, B captured. Our disagreement distribution wheel uses 2 overlapped rectangles to encode this information. Assume this rectangle is A+, and this rectangle is B+. Their overlapped and non-overlapped regions intuitively reflect the size of the 3 cells. Specifically, among the 2 sets of 380K merchants, around 133K are captured by both models. Around 240K are considered as restaurant by model A, but considered as non-restaurant by model B. So the size of the A plus B minus cell is 240K. Similarly, the A minus B plus cell is also 240K. The size of the two non-overlapped regions may not be exactly the same, but should be similar if the two models have similar performance. This balance between the disagreed predictions is good for us to learn from their disagreement. If using different thresholds from step 2, the 3 cells will have different sizes. We use the 3 bar charts to denote the size of the 3 cells across all possible thresholds to provide an overview of the cell sizes. Back to our encoding with 2 overlapped rectangles, we will have 3 bar charts in the overlapped and the 2 non-overlapped regions. To continue our earlier case, let's assume the cutoff here is 10% and we have concrete sizes of the 3 cells. Each cell can be divided into 2 cells at step 4 based on the true label of the merchants. For example, among the 133K both captured merchants, about 54K are correctly captured, meaning those merchants are restaurants and both models also predicted them as restaurants. That is, true positives. However, the rest 78K are miscaptured, meaning they are not restaurant, but the two models both incorrectly predicted them as restaurants. That is, false positives. The A plus B minus and A minus B plus cells can be divided similarly. And to the end of this step, we have 2 disagreement matrices. Our disagreement distribution wheel allows users to change the cutoff at step 2 and watch the size change of all the 6 cells. At step 5, we train a discriminator to differentiate merchants from the 2 disagreed cells. This is the learning part of the framework. The discriminator here is just a binary classifier. As the data features used to train model A and B are usually not available during comparison, we ask users to propose a set of meta features at this step. The meta features can be based on users' prior knowledge on the 2 models. For example, when comparing the tree and the RNN model, the sequence length of individual merchant is a good meta feature. The RNN may behave better on instances with longer sequences or richer sequential information. Based on this, we propose a meta feature counting the number of days a merchant has approved transactions over the past 2.5 years. This meta feature reviews the number of service activities of the merchant, reviewing its temporal active level and the richness of its temporal behaviors. We can also compute the average number of approved transactions per merchant, the number of declined transactions, and the meta feature list can keep growing. Note that one can propose any meta features to probe the two compared models' behaviors, even if they have no knowledge on the two models. Using those meta features, we train two discriminators for the disagreed merchants from the true positive and false positive cells. Specifically, the two discriminators are trained with tabular data. Each row is a merchant. Each column is a meta feature. And the label of each row is either A plus B minus or A minus B plus. Step 6 adopts an overview plus detail visualization to interpret the discriminators, using the sharp value of different meta features. From the visual interpretation, actionable insight could be derived. From the visualization, we can rank the meta features to identify the important ones based on different metrics. Let's focus on the true positive discriminator on the left side and rank the meta features by the overall metric. The meta feature that counting the number of days with approved transactions rank the third. Clicking the feature, we can check its details on the right. As we have 2.5 years of the transaction data, the possible value of this meta feature ranges from 0 to 912 days. However, for the two sets of disagreed instances, the value of this meta feature ranges from 22 to 911 days. Bubbles on the right are more likely to be from the tree minus RNN plus cell, and most of them are in orange. This means the RNN correctly captures restaurants with more active behaviors in the past 2.5 years. In contrast, the blue bubbles on the left indicate merchants with less active service behaviors, and the tree model behaves better on them. This observation matches well with our expectations and reveals the strengths of the RNN model. Knowing this difference between the two models directly leads to better model selection based on the service frequency of the merchants. From the visualization, we can easily adjust the color mapping. Select bubbles in different value ranges from the legend. We can also change the layout of the bubbles by using the circle packing algorithm or the force-directed layout. Changing the number of bins when constructing the 2D histogram allows us to control the number of bubbles and the bubble sizes. The meta feature list for the false positive discriminators can be analyzed similarly, and the two sets of meta features are linked with curves to track their importance across the discriminators. We have also compared multiple other model pairs in different problems. Please check those details from our paper. Thanks for watching.